Now that we know the fundamentals of controlling the tool with our CNC code, there's some other considerations that you need to take into account. When we think of the tooling, we think of geometry, and that geometry coming into contact with the material to produce the surface of interest. Now, the important thing to consider here is what are the cutting surfaces of the tool, and they will depend upon the type of tool that you use. So we'll look at the flat end mill as an example, and also the ball end mill, different geometries and different cutting surfaces. Some of the characteristics that you will note first are the number of flutes. So when we select tooling, one of the questions that we need to address is how many flutes should we define for our tooling, what should be the diameter of the tool, and of course this is going to be affected by the feature that we're trying to create. So that diameter, we might consider having the largest diameter possible, but here we're bounded by the minimum feature radius because we can't go any larger than that, and so we might have to do tool changes as we go through our paths. Also keep in mind that the deflection of the tool that we'll look at a little bit later is going to be inversely proportional to the diameter. So that suggests, of course, to have the largest diameter possible to minimize tool deflection, and tool deflection is going to contribute to deviations from nominal. So we already recognize that there are going to be certain deviations, and one contribution will be the tool deflection. The length of the tool must also be considered because that will be related to the depth of the feature. So if we're going to be cutting surfaces to a given depth, then we have to make sure that the cutting surfaces on the tool are sufficient to cover that entire depth. And also tool deflection is not only related to diameter, but also will be proportional to length. The longer the tool, the greater likelihood you're going to have some type of tool deflection. When you look at the deflection problem, you can think of the tool that is attached to the collet, which in turn is attached to the spindle, and now we're coming into contact with the workpiece here. By moving it into the workpiece, you can see here we've got an opposing force, the workpiece itself, and we've got the force of the spindle moving it into that workpiece. What's going to happen here is the classic cantilever beam deflection problem, because as you can see here, we're going to have a moment, and that moment is going to try to deflect the tip of this tool, which, if you recall from moments, will be dependent upon the length of the tool. Also, the material itself, the modulus of elasticity, so what type of material is used in the tool, and it's going to be proportional, the amount of that deflection, to L cubed. So you can see that L has a profound impact because of the exponent here on the resultant tool deflection. Now this suggests, of course, that you want to minimize L and therefore have the smallest length possible and still be able to create the feature of interest. And of course, how deep this is in the collet will also affect that. So the mounting of the tool in the collet is important as well. When you look at an end mill, and this is a classical depiction of the end mill, you note that there are many characteristics of that. First of all, you should note where the cutting surfaces are. So over the length of the cut here, we can create our feature, and so part of the specification has to be related to all the features we're creating with this end mill. So here we have the side cutting surface, and then if we look at it from the bottom view, we note that we also have a cutting surface here that's related to the number of flutes. So the number of flutes is going to be important, as we'll see, because that affects the resultant characteristics of the surfaces. And then we have some other characteristics here that will be related to the material removal process. The cutting diameter, of course, will be related to your tool offsets, and it will also affect how fast you can remove material along the cutting path. When you think of the surfaces that you are removing material from, for the end mill case, we note that there's a plane normal to the spindle, and of course there are an infinite number of planes that are normal to the spindle, and that's depicted by this line here. So if you can imagine all the planes possible that are normal, or you can think of it being again a surface that represents a pocket or some type of depth feature. Then we have our planes that are parallel to the spindle and tangent to the tool, and again here there could be an infinite number of these planes moving around radially with the tool. So all these surfaces are possible based upon the machine configuration, and now it's a question of moving the tool along a tool path and creating that planar surface. Of course, if we're moving in an arc or we want to do a free-form curve, we can do that as well. Essentially, it would be composed of an infinite number of planes. Again, these planes represent surfaces that are going to come in contact with the tool. For a ball end mill, we typically use that if we have free-form curved surfaces. And as you can see, the configuration here is different in this region of the geometry. And here we have a hemisphere of cutting surfaces so that we can create a cutting plane tangent to the ball end mill. And that allows us to have 3 rotational degrees of freedom. So as you can see here, this line depicting a plane coming into contact with that surface. And of course, we can have an infinite number that are tangent to that. So we can create extremely smooth surfaces in terms of curved surfaces with this tool configuration. When you look at the flute characteristics of the ball end mill or standard end mill, here we compare 2 flutes versus 4 flutes, and clearly the flutes are going to regulate how chips are removed as we move across the surface of the material. As the flutes decrease, we have wider channels and therefore better chip removal. Typically, it's good for soft materials and when you're using the lower feed rates. As I increase the number of flutes, what we're going to see as a disadvantage here is the potential, depending upon the material and the cutting parameters, to build up chips in the features. And of course, that can affect the surfaces that we're creating. The nice thing with the 4 flute is we can move at higher feed rates, and typically it's better for harder materials. You'll also encounter less tool chatter and deflection, and it's also good for fine cuts. So selecting the proper tool with the right number of flutes will depend upon the nature of the materials and the machining parameters. The other thing you might want to consider here, and this is from an article by MacArthur in Mold Making Technology, is that when the tool comes in contact with the material, there's also the potential for heat generation. Now, of course, we can be spraying coolant continuously on the material, and hopefully that heat generation is greatly reduced, but of course there's always the potential for heat being produced in this region as we come in contact with that material. Well, as you know from basic physics, this is going to affect both the part, because as we heat the material, it's going to expand, as well as tool surfaces. As they heat up, they will expand, and this will contribute to your process capability because the dimensional characteristics of the material have changed while you're cutting them. So if I look at removing material in either one of these cases, one of the questions that we might have is on which side of the part should the tool travel. And so here we see the cutting surface. We're rotating in this direction, and as we remove that material, this region is being heated as we move in that direction. The other thing that we haven't mentioned is many tools have coatings on them, and that coating is meant to improve the tool life. If we look at heating and cooling cycles as we're machining, you can see here that cycling will cause some heat accumulation, and if that heat is not reduced, then we're going to get a breakdown in the coating. And you can see here there's a threshold at which the coating will begin to break down, and then it will no longer be effective. So what we'd like to do is keep below that threshold by having some continuous cooling, which may be due to our coolant on the material or the way in which we are cutting. So careful consideration has to be given to the type of cutting that you're performing. When you look at the cutting surface and the rotation of the tool, as you can see here looking at the bottom of the end mill, the spindle rotation plus the tool cutting surfaces are going to affect, again, how that material is being removed and how it is being heated in terms of that cycling. It will also affect how chips are being formed, and that has to do with how the surface is entering the material. Typically, the width of your cut is going to be less than 2/3 of the diameter, and that is kind of a rule of thumb. And then if we look in the Z direction, looking down the spindle, if it's a vertical mill, your depth of cut is usually 1/3 of the diameter or less. And then if we view this spindle as turning clockwise, again from the bottom view it looks like it's counterclockwise, but if it's turning clockwise, then we have two alternatives: climb milling or standard milling, depending on how we are moving with respect to the workpiece. So this is going to tie into your G41 and G42. If we look at standard milling, again looking at a bottom view of our tool with respect to the workpiece, you can see here our tool direction. We're moving along the surface here, and we're entering at this region of our workpiece, and then we're exiting here. If you look at that with respect to your tool compensation, the G42, you can see we're moving to the right of the workpiece from the top view, or the workpiece is to our left. What's going to happen here is that tool wear will be greater than climb milling, except when we have rough surfaces. And the direction vector here in which we're moving is the same as the direction in which the chip is forming. And you know about chip formation from 248. So the width of the chip starts from 0 and then will increase, and we tend to have an upward force on the cutter, which means it will affect how that workpiece is fixtured. More power is going to be required because of how the chip is being formed, and the surface finish can be marred from the chips themselves. So chips are going to separate from the workpiece in front of the cutting surface, and oftentimes we do this standard milling with rough surfaces such as found in sand castings or forgings. Climb milling, on the other hand, again looking from the bottom of the tool surface, the cutting surface, is entering at the top here of the workpiece and then rotating into the material. If you look at it from your CNC code, this would correspond to a G41, where again we are to the left of the workpiece looking from the top. The direction vector in terms of motion of the tool is the opposite of the chip formation direction. So our chips are forming in this direction, but the tool is moving in this direction. And the entry chip thickness is wider than the exit thickness. Turns out that this tends to produce a better surface finish, and going back to the heating cycles, it will help reduce the heating of the surface. The chips will be removed behind the cutter, and people have found that it can increase the tool life in some cases by up to 50%. As we said, you end up typically with a better surface finish. So selecting G41 or G42 is not just a matter of moving around the surfaces that you're cutting in a certain direction, but it also has an impact on the resultant surfaces and the life of the tool, as well as the coating. Revisiting that G41 and G42, we have to think about how the machine actually compensates when you issue that G41 and G42. So there is some time that it takes for the initialization of the tool offset that we haven't mentioned before. And the tool compensation is actually taking effect during the following move. So the compensation will be based upon the set of points that you select for your move, because what's happening here is the controller is looking ahead to the next move. So here we've moved the tool off of the workpiece, and the reason for that is before I use tool compensation, there's some finite time for us to interpolate from its current location to where it should be based on the direction of the move. So if I wanted to move to this location, I need to move a minimum of the radius, and that's probably not a good idea because you're cutting it close there. So I need to move off of that surface and then do a move, as you can see here, with my G41 to a X20 Y20 and then a G01 Y40. So this X20 Y20 corresponds to this coordinate here, and then this corner up here is going to correspond to 2040. So if that's what I need to do, of course I need to be offset from that surface before I make that move. Otherwise, what could happen is I could end up with the incorrect offset and end up cutting into that corner. Well, there's really an infinite number of offsets that you could consider. We can start the tool here, 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 and so forth, as long as we're far enough away. So when this compensation takes effect, by the time we get to X20, Y20, we're actually in the correct tool offset. So here you can see the tool moving along without tool compensation. So we end up with the center of the tool at the corner, and that's obviously not what we want. The red vector is indicating what happens when the G41 is initialized, and over the course of the move we are linearly offsetting the tool until we get to that corner, and now we're at the correct offset. So when we move to our Y40, we're creating the surface that we intended. Key concepts here, of course, tool deflection. That's going to affect your process capability. The direction in which the cutting surface enters the material, climb milling versus standard milling, affects the outcome that you're going to produce on that surface. And then the offset for tool compensation must be considered before the tool reaches its first position. Otherwise, you're going to end up with problems in terms of removing material that you didn't want to remove. So in summary, you have to consider the tool characteristics because they will affect your resultant machine surfaces. G41 and G42 are going to be related to the type of milling, climb milling and standard milling. And the tool compensation requires that initial move before the tool offset is in full effect.